Good evening, everyone. We want to continue our discussion on chi-square. Was it last? Yes, today is Tuesday. Last week on Thursday, we started our discussion and some historical background. Then we also some preambles, the origin of chi-square, and different some of those statistics that follow chi-square distribution. We also talk about degree of freedom as applied to chi-square. So specifically now we want to go into some of those specific chi-square, then look at how they are calculated, then how you can use software, especially SPSS, to run some of them. So if you remember, for some of us, though in my lecture and workshop, I don't actually flag what do I call it, formula. But I've already told us that the statistics, they are actually the same thing. Hypothesis tests, they are the same thing, put in different cloth. So you see this element of division. There's aspect of it that will be numerator, and the aspect that is denominator. It's the same thing. We say the denominator is the difference, is the signal, the difference you want to look at. The denominator is the noise, which is the measure of inherent variability or standard error. So the statistics, most of the time, if it's going to be significant, it will be higher, far higher than 1, greater than 1, except the non-parametric counterpart of t-test, which is in the reverse direction. So this is chi-square you are used to. I'm sure many people are we are all used to chi-square. You say that sigma observed minus expected square over expected. Chi-square is just something like x square. That is what we use to denote chi-square. Chi-square, the thing is not just, it's a Greek letter. It's not x, chi. Chi-square, you square it then. Sigma means summation of observed value minus expected value. You square over expected value. So for each of the cells, we already concluded that chi-square depends on contingency table. Most of the chi-square, not all per se. For example, at least for the Pearson chi-square we're going to calculate first, it really depends on contingency table in the sense that since we use it to look at association between two categorical variables. So when you say something categorical, it means that the value are in category. For example, sex, there are 2 categories, male and female. For ethnicity, in our environment, we usually reduce it to 4 categories. In Nigeria, you say Hausa, Igbo, Yoruba, others. So we may have geopolitical zone. There are 6 categories in the country. We may say religion. We usually have Christianity, Islam, then traditional, then we can have other. So that is the nature of categorical variable. Unlike numerical variable, where you have many numbers, and in that situation, for you to bring it to categories, manageable category, you have to range the value. So of course, any numerical variable you have ranged, it has become categorical. For example, age is numerical variable, but when you begin to have range, you say, oh, less than 20, 20 to 24, 25 to 29, whatever. If you have 5 or 6, whatever number of category you have already changed it to age group, and that age group is a categorical variable. So we are looking at association between 2 categorical variables. It's good for you to represent by 2 by 2 table, where you arrange the category of 1 along the column, arrange the category of the other one along the row. So the number of cells at the cross section here will be the number of cells. So we have already said that the lowest one is 2 by 2, when you have both exposure and outcome, two categories. Like for example now, sex, male or female, employment status, women or female. Want to know the employment status of maybe you see how sex influence employment status. So both of them are two categories. So it gives you the simplest form of contingency, which is 2 by 2. We look at it last week. Now, you will see that for each of the cell, you have the observed value. We are going to go into it now. We have the expected value. It's the observed value, you remove the expected value, we square it. I will tell you the reason we square as we are going on. It's not far-fetched from what we have seen before. So sigma means the sum up. O being each observed value, actual value, that's the actual value in the cell. E, each expected value, which we calculate the category and say observed minus expected, we square over expected for each pair of the observed and expected value. Then we send them up. Or for each pair that is in the cell, each cell has observed value, expected value. So that's what we do. Observed minus expected, square over expected for each of them. We sum it up. That's chi-square. And this is very simple. And let's move forward to, so for example, look at what I was talking about. This is the example we showed the other time, sex and employment status. This is the simplest form that can come to us. You will see that the total, if you look at this table now, the first table, that's the one that gives us the raw. The raw in the sense that the raw values, there are 300 people involved. If you look at the last cell to the left, is 300. There are 300 people. Out of these 300 people, we put the sex along the row and employment status along the column. The sex is either male or female. Employment status is either employed or not employed. If you look at the conventionally, it makes sense to put the exposure variable along the row and outcome variable along the column. That's what we have done now. If you do otherwise, it doesn't change the chi-square. You calculate it, either you use how to calculate it or you use software, it gives you the same thing. But you may have issue interpreting it. As you are going to see, I'm going to go through each of those things in detail. As I told you before, chi-square looks simple because it's a common thing we hear of chi-square. It's not as simple as you think. In fact, understanding theta is far, far simpler than chi-square. The people among up to chi-square say, they have heard of chi-square. But the issue there is that apart from the fact that there are many statistics that followed chi-square, that is, we have many different types of chi-square. You're going to see that if for each of them, understanding the logic behind it, is not as simple compared with the t-test. Now, you will see that for male, the total male is 130. The total female is 170. Of course, when you had 130 and 170, it gives you 300, which is the total. Then if you look at it from the perspective of the employment status, the total employee is 185, the total non-employed is 115. If you add it together also in that direction, it gives you 300. Whichever way you get 300. Now, all these one, the total male and female, the total employed and non-employed, they are the total. They are not part of the cell. That's why I color code the cell. The green aspect, that is the cell. We have 4 cells here now. The number 1 is we have male that are employed. We have male that are not employed, which is 40. Male that are employed, 90. Male not employed, 40. Female that are employed, 95. Female not employed, 75. Can you see now? So if you see add all of them together, they give you the 300. But if you want to know how many, according to sex, give you 130, 170. According to employment, 185, 115, it's the same 300. So what you have in the green, 90, 40, 95, and 75, they are the observed value. Those are the observed. That's what you observe. In the raw data you have, when you summarize your data, you discover that there are 130 male, 170 female, 185 employed, 115 not employed in this. So when you further broke them down into male employed, male not employed, female employed, female not employed, those value in the green, 90, 40, 95, 75 are the observed value. Now, the logic behind this expected value, so this is what you observe. But you can see if they ask you now, you may mistakenly say, oh, which one is more employed? If I ask you now, which one is more employed? Maybe I should ask, because it's a lecture. So if let's say it's physical, it can be interactive. You can make it as interactive as possible. You can unmute. So among male and female, which category is more employed? Because we have already concluded that male is the exposure, female, sex is the exposure, employment status is the outcome. So what we are looking at among the female, how many are employed? Among the male, how many are employed? We want to compare them to really know which one is more employed. We are not interested in saying among the people that are employed, how many are male and female. So it's different direction. We are not interested in that. Among non-employed, how many are female or male? No. What we are looking among the male, how many employed, how many non-employed? Among the female, how many employed, how many non-employed? Because male and female is push. So we want to know the outcome for each of the categories. So if I ask you now, who will tell me who is more employed, male or female? Now somebody say, who is more employed?
Male is more employed.
So why?
I'll say male is more employed because.
Good evening, sir.
I
would say females are more employed.
So what's the reason?
95 of females are employed, while 75. Okay.
The total number is more.
Total,
more
90 out of 130.
Yeah, 90 out of
130.
More than 95 out of 170.
95 out of 170. Okay. On that basis, we can say male, sir.
Yeah, that's great. You are right. Male are more employed because if you try to calculate the percentage, relative frequency, that is 95 of female over the total 170, then 90 of male over 130. You see that the percentage of 90 over 130 is higher than 95 over 170. So you can say the proportion employed among the male is higher than that of the female. Thank you. So that is what you have observed. Observed value now. Based on your observed value, even translating into percentage, you can see that it shows that male are more employed. So what we now want to observe, we can see now there's a difference. That is, in this difference now, male are more employed. If there's no difference, you just show that, oh, both of them will have the same proportion. And that's, oh, no, there's no one that is more employed than the other. There's no difference. But we have observed this difference now. So what you want to now, why do you want to do tests? You want to test to say that this difference I have observed, is it due to chance? This difference may be just chance occurrence. If it is chance occurrence, it just happen like that. If you redo this thing now, maybe you recollect your data, you may find that maybe it may change. You may have more female being employed than male. So in order for you to validate this difference, I observed that male is more employed than female. Is it due to chance? So at the end of the day, we're going to have a statistic, which is this chi-square. I'm going to have a corresponding measure of the probability, which is the p-value, that show that, oh, this is the probability that the difference I've observed is due to chance. It's not a true difference. If something just happen like that, that shows that it's not a true difference. And that is why the higher the probability, the less likely there's a difference. So if the probability is high that, oh, it's just due to chance occurrence, it means that, oh no, there's no actually difference in the employment status between male and female. So when the probability is, let's say the probability is 1, p-value is 1, it means that it's certain that it's due to chance. That shows that there's no difference between employment status between male and female. Even if it is not equal to 1, if it is close to that 1, 0.5, 0.6, 0.7, even to the extent that if it's greater than 0.05, because 1 out of 20, which is 5%, which is the same thing as 0.05, is the benchmark. So any value probability that is greater than that, no, we not say no, forget. It's due to chance. The probability is too high. But if it is not less, so extremely small, like less than 0.05 or 0.05 or less, we now say, oh, the probability that this difference is due to chance is so negligible. Let's just assume that it's not due to chance. There's a real difference that actually may statistically is slightly the employment status among May statistically higher. So let's look at the way it works. Now we have our observed value here. Now, even though in trying to see if he may or more is employed or more, we try to translate to proportion, but the whole number 90, 40, 95, 75. Now we need to know whether this difference is significant or not, is due to chance or not. Remember also that probability is probability of committing type 1 error. I will not go back because we are talking about, if you listen to the video again for that introduction to inferential statistics, I talk about it very well. Now, let's look at what do we do. We want to know there is this, if actually there's no difference between male and female, what should be the value inside those green areas? If there's no difference at all, if the employment status is exactly the same for male and female, what should we should know that yes, there are 300 people, there are 130 male, there are 170 female, there are 185 people that are employed, there are 115 that are employed. All those total around are still fixed. But what changes do we expect around the green, those 4 cells? What value should be there in those 4 cells for you to now conclude that no, there's no difference at all between male and female when it comes to employment status? And that value is what we call expected value. Expected value is the same thing as hypothesized value. It means the value when non-hypothesis is true. Non-hypothesis is true when there is no difference in the employment status between male and female. Because non-hypothesis say there is no difference. There is no difference between in the employment status between male and female. That's what the non-hypothesis will say. So if actually that is true, the value that will be there is what we call expected value or hypothesized value. To give you some clue, naturally when we do things, especially when we summarize quantitative variable, wherever we give mean, we say mean is this. That mean is expected value, is hypothesized value. What does it mean? When we had all our age, maybe the ages together, maybe we are 20 in this class, we had all the age together, we get the value, total value for adding all our age together. We now divide by 20, since we are 20, we get the average. We now say that average. That is, if you give each of these average to each person, it will still give us the total value. Is the total value you divide equally among the 20 people. So if the mean means that there's no difference, if we give the mean, that value to each of the 20 of us, that shows that we have the same age. We have the same age. That means that that is not hypothesis. That is, there's no difference in our age, in age of every one of us. So mean is a crude model. There is an hypothesized value that, oh, there is no difference. So when you add everything together, you calculate mean. You are saying that this is a crude model. You are saying that this is the value of the age of each person, if not hypothesis, like no different in our ages. Does it make sense? It's like pulling all the money together from everybody and then divide equally. Everybody has the same thing. That is the mean average. Can you see the logic? There's video I explained that. Let's move further in what we are saying now. How do we get the hypothesized value, which is the expected value? If we go to the next table, you see what we do. You will see that you have to calculate for each of the cells, and that's what I've calculated there. For cell, you will see the logic behind it is that we have 130 male out of 300 people. You see, okay, what proportion is telling you that the proportion contributed by May to the total is 130 out of 30, 130 over 30. And the total that I employ. So you want to know the value that people make, the number that should be made,